In Section 8, we investigate another type of logarithm with a base that is very common that we use in mathematics, statistics, probability. Rather than base 10, there is an irrational number called e, kind of like we have that irrational number pi. And it's involved in statistics, probability, growth, and decay. E has been calculated to hundreds of thousands of decimal places, and just like pi, there is no repetition, there's no pattern, there's no block that repeats. It's an infinite decimal. First couple of decimal places, if you're curious, are 2.718281828. And before you think there's a pattern there, no, 459, then it keeps going, and there's nothing that repeats. If we have a logarithm that's base e rather than base 10, we call that natural logarithms. And we might write it as lowercase l, then n, and then our variable x. And in the old days, we would look these up in a table, just like we would look up logs base 10. But we're going to pass over that and use our calculators. Much more efficient, because again, quite often the number we were looking for was not there, and we had to do extra work to find our answer. So we're going to do that. But we're going to practice rewriting the following natural logs in exponential form and the following exponents in natural logarithmic form. So again, writing an exponent as a log as an exponent. Remember, natural logs are base e. So typically, I don't have to write this e. Just ln. That's good enough. But for now, I'm writing it just as a reminder. This is a log base e. It's not a natural log base e. That might be confusing to some of you. So I wrote that because otherwise some of you will say, well, how can I write it as an exponent since there's no base? Well, let me remind you, this is implied that the base is e. So to rewrite this, it's the base e to the 5th power is equal to x. Okay, how about this? E to the x equals 7. Rewrite that as a log. Well, x, remember the exponent is the log of that number 7, and it's base e, and I'm not writing that base e there. Natural log of 12 equals x. Well, remember, it's base e. So to rewrite it, that's e to the x power is equal to 12. We learned this early on in the chapter, how to rewrite logs as exponents and exponents as logs. All right, let's start simplifying before we go much further. Natural log of 1 over e squared. Well, remember that negative exponents means take the reciprocal. So instead of 1 over e squared, let me call that e to the negative 2 power. And this we should be able to do in our head if we remember that the base here is base e. E to what power is e to the negative 2 power. But if you don't remember that, when you got the log of a number raised to a power, that's the same as the power times the log of the number. And the natural log of e is 1. The reason for that is the natural log and e to some power are inverse operations of each other, because that asks the question, e to what power is e to the 1st power? Because remember, logarithms are looking for exponents. So the natural log of e is 1. 1 times negative 2 is negative 2. And we could have answered that question earlier. E to what power is e to the negative 2 power? That's negative 2. Write this as a single logarithm, so we've got to practice our laws of logs that we learned earlier this chapter. So when you have a number times a log, that number is the power that the 5 is being raised to. So the natural log of 5 squared is the same as 2 times the natural log of 5. Now this one's a little tricky. There's no natural log here. How can I write that? Well, remember just a moment ago we said the natural log of e is 1. So let me write negative 3 as negative 3 times 1, and that 1 is going to be the natural log of e. Now each term has a natural log in it. Well, let's just simplify. 5 squared is 25. And when you have a number times a log, that number is the power that we're raising to. Remember that when we're adding two logs of the same base, that's the same as the log of their product. So 25 times 4. 25 times 4 is 100. And then when we're subtracting two logs with the same base, remember that's the same as the quotient. So that's the natural log of 100 divided by e cubed. That's using our properties of logs forwards and backwards. All right, we need our calculators here, and let's try to find some natural logs on your calculators and some inverses. Find the natural log of 5.24. Well, depending on your calculator, you will type the 5.24 first and then hit the natural log button. Or you'll need to hit the natural log function first and then the 5.24, and then you might have to hit enter, equal, or execute. Round that to 4 places, just like we did with logs base 10. That's approximately 1.6563. How about the natural log of 0.001277? Well, on the table of logs, we'd have to convert that to scientific notation. But on our calculators, whether you type log first or the number first, you do that. Type the number, type the function, round it to 4 places, so that's negative 6.6632. How about the natural log of 1,234? Well, again, type the number or the log first and the other one second. Round that to 4 places, so that's approximately 7.1180. How about e to the first power? Well, on your calculator, where you have the natural log function, you may have e to the x above it written in a different color. Newer calculators may not have that. You may have to choose these functions from a menu choice. But in this case, they're inverse functions of each other. So you would, whatever color this e to the x button is, you're going to look for your second function, third function, inverse, or shift. That's the same color. And so you'll type 1. You'll hit that second or third or shift or inverse button, then the e to the x. And you will round this to approximately 4 places, 2.71828. Actually went 5 places. All right, how about e to the 1.23 power? Well, we do that the same way. Depending on your calculator, you might have to hit the function for e to the x first, or you might have to hit the number 1.23 first. But when you hit the number and the function, round that to 4 places, that's approximately 3.4212. All right, let's start solving some equations with natural logs in them. Solve the natural log of x equals 2. Now, what we're saying is there's some mystery number. We typed into our calculator, we took the natural log of it, and we got 2. What is that mystery number? Well, remember, we don't know how to solve this. And if you don't know how to solve something in logarithmic notation, rewrite it in exponential notation. What's the base? Well, it's invisible here because natural logs are base e. So e to the second power is equal to x. Grab your calculator. Just like we did a second ago, we're going to use this e to the x function on your calculator. Type 2, hit the e to the x function, round that to 4 places, 7.3891. All right, how about the log of the reciprocal of some number equals 2? Well, no tough problem. The base e to the power 2 is 1 over x. And we can take the reciprocal of both sides of the equation. That's what I did here, and I also swapped sides. So x would be on the left. The reciprocal of 1 over x is x. The reciprocal of e to the second power is 1 over e to the second power. And we can rewrite that using negative exponents as e to the negative 2 power. Calculator to the rescue, type the negative 2, hit that e to the x button, round our answer to 4 places, 0.1353. All right, let's solve this equation. E to the 2x power equals 9. Maybe we don't know how to solve this in exponential form. Perhaps we should rewrite it as a logarithm. Or actually, we can take the natural log of both sides, just like we could take log base 10 of both sides of the equation. So let's do that. Natural log of the left side, natural log of the right side. On the left, when you have the log of a number raised to a power, that turns that power into a factor times the natural log of e. Remember, the natural log of e is just 1. And when we use our calculator, type 9 and find the natural log of that, round that to 4 places, is approximately 2.1972. And to get x by itself, divide both sides by 2. And round this to 4 places again, so that's 1.0986. And that's our look at exponential functions base e and natural logarithms, which are logarithms base e as well.